In this video, we're going to complete the KutaSoftware Infinite Calculus free worksheet function inverses. Now for numbers 1 through 4, we're to state if the given functions are inverses. And one way to tell if a function is an inverse of another function, when given what those functions are equal to, we're simply going to plug in one function into the other in terms of x. So we have g of x and f of x, so we can do g of f of x, f of g of x, we will get x as our solution. And if that's the case, if that is true, then the functions are inverses of one another. If it's not, then they are not inverses. So looking at number 1, I'll do g of f of x. So I'm going to take the function f of x and plug it into g. So f of x is negative 6x minus 1. So g of f of x will be g of negative 6x minus 1. So I'm taking negative 6x minus 1 and plugging it in for x in g of x. So then we'll have negative 4 times negative 6x minus 1, distributing that negative 4 to negative 6x and to the 1. Negative 4 times negative 6x is a positive 24x, and negative 4 times 1 is negative 4, and if we're subtracting a negative, it's the same as adding a positive. So you have 24x plus 4, which cannot be simplified any further, and that is not equivalent to x. Therefore, no, in number 1, we do not have inverses. And before moving on, I want to note that when we're testing to see if functions are inverses of one another, we have to complete both ways. Both ways, g of f of x or f of g of x, have to equal x. But as soon as you can show that one way does not equal x, you do not have to also show that the other way does or doesn't equal x. Because once one of these, either g of f of x or f of g of x, does not equal x, then it's not an inverse. So let's continue on to number 2. On number 2, we have to show that h of f of n equals that variable n, and we must show that f of h of n equals that variable n. But if we want to, we can switch this in to our variable x. So I'll go ahead and do that. So we're going to see if h of f of x equals x. And we need to see if f of h of x also equals x. If both are true, then those functions are inverses of one another. But quickly, I'd like to note we do not have to switch this variable in to x. I just did so because n sometimes looks like an h when writing on my tablet. So I'll start with h of f of x. So we'll have h of f of x, which f of x is negative 5 plus 9 halves times x. Now I'll plug h of negative 5 plus 9 halves times x into my variable within my h of n function. So that's going to equal 2/9 times negative 5 plus 9 halves x plus 10/9. And you can see here is what I'm plugging into the function, and there was my variable that I plugged it in for. Now I'll simplify to solve. I'll distribute this 2/9. 2/9 times negative 5 is going to be negative 10/9, plus 2/9 times 9 halves times x is going to be 1x, or simply x, and then we're adding 10/9 to that, and you can see that negative 10/9 and positive 10/9 will cancel out to leave me with x. So far, h of f of x does indeed equal x. Now we have to see if f of h of x equals x. So we're going to have f of 2/9 times x plus 10/9, and that's going to be negative 5 plus 9 halves times what we're entering into that function. So negative 5 plus 9 halves times 2 ninths x plus 10 ninths. So we're going to need to distribute this 9 halves to both the 2 ninths and the 10 ninths. So we'll have negative 5 plus 9 halves times 2 ninths, which is 1, times x will be simply x, plus 9 halves times 10 ninths will leave me with 10 over 2, which I know is a positive 5. So we have negative 5 plus x plus 5, which equals a positive x. So in number 2, f of h of x also equals x. Therefore, since both h of f of x and f of h of x equal x, then these functions are indeed inverses. So the answer in number 2 is yes. Now on to number 3, g of n and f of n. So first we're going to see if g of f of n equals n. And in order to do that, I'm going to take my function g and plug in f of n. So that's going to be negative 4 over n plus 2. So plugging that in for my n and g of n, I'll have 4 over the opposite of negative 4 over n plus 2, and then we're adding 2 again. So that's going to equal 4 over the opposite of negative 4 over n plus 2 is going to be a positive 4 over n minus 2, and then we're adding 2. Negative 2 plus 2 is 0, so I'll get 4 over 4 over n, but remember, dividing by a fraction is the same as multiplying by that reciprocal, so we'll have 4 times n over 4, which 4 divided by 4 is 1, so we get n for g of f of n, completing our first step. Now, we need to see if f of g of n equals n. And just so you can see this a little bit visually, I'm going to mix up the colors of g of n. So we're plugging in g of n for f, and we're going to see if that equals n. So I'll have f of the function g of n, which is 4 over negative n plus 2. So I'm going to take 4 over negative n plus 2 and plug that into the function. So I'll have negative 4 over 4 over negative n plus 2, and I'll be adding 2 to that. So you can see that the entire function g of n was plugged in for n in my function f of n. Now, just like before, when we're dividing by a fraction, it's the same as multiplying by a reciprocal. So I'm going to rewrite this as negative 4 times negative n plus 2 over 4, and then we'll add 2. So you can see that negative 4 and 4 will cancel out to leave me with negative 1, because negative 4 divided by 4 is a negative 1. So we'll have negative 1 times negative n plus 2, and when I distribute that negative, I'll get positive n minus 2 plus 2, which, if I'm subtracting 2 and then adding 2, those will equal 0, and 0 plus n is equal to n. So again, I've shown that plugging one function into the other gives me the variable n. And because both are true, then these are indeed inverses. And now on to number 4. And number 4, let's start and see if g of f of x equals x. So I'm going to take g and plug in f of x, which is negative 4 minus 4/5 x. Does that equal x? So for g of x, we'll have 10 over 7, but as opposed to using x, we're plugging in f of x. So 10/7 times negative 4 minus 4/5 x, and then we're subtracting 15/7. So I'll start by distributing my 10/7. So 10/7 times negative 4 will be negative 40/7, and then I'll be subtracting 10/7 times 4/5, which is 40/35 times x, and then I'm subtracting 15/7. Now I'll combine my like terms, negative 40/7 and 15/7. So negative 40/7 minus 15/7 is going to be negative 55/7. And I'm still subtracting 40/35x. However, this does not simplify any further and does not equal x. Therefore, no, my functions are not inverses of each other, because I already proved it wrong going one way. Now for numbers 5 through 10, we're going to be finding the inverse of each function. And there's a simple way to find the inverse given one function. So for our first step, we're going to plug y in as the function. So looking at number 5, h of x, we're going to make that y. So we'll have y equal to 3 over negative x minus 2. Our next step, we're going to switch x and y. So y becomes x and x becomes y. So now, switching x and y, we'll have x equal to 3 over negative y minus 2. Then for our third step, we're solving for y. So in order to solve for y, we're going to need to get y out of the denominator. So I'll multiply both sides by negative y minus 2. So you can see I'll have negative y minus 2 times x equal to 3. Now my next step, you may want to distribute this x, but don't, because you want to get y by itself, and in order to do that, you'll want to move your other variable to the other side. So I'll divide both sides by x to get that negative y minus 2 equals 3 over x. My next step, I'll add 2 to both sides to get that negative y equals 3 over x plus 2. And then lastly, I want this y to be positive, so I'll multiply both sides by a negative 1. So we'll have that positive y equals negative 3 over x minus 2. So now we've solved for y. And for our last step, number 4, we need to set y as the inverse function. So because this function was h of x, y now becomes the inverse of h of x. So the format is h superscript negative 1 x. That's read as the inverse of h of x, and that equals negative 3 over x minus 2. So this is the inverse function of h of x, negative 3 over x minus 2. Now remembering our steps 1 through 4, let's complete number 6. So let's do the first step. We're going to plug y in as the function. So f of x, I'm going to plug in y. So y equals 2/7 x minus 10/7. Now I'm going to switch x and y. So we'll have that x equals 2/7 y minus 10/7. Now for the hardest step, I'm going to be solving for y. So I'm going to add 10/7 to each side. So I'll have x plus 10/7 equal to 2/7 times y. And now, in order to isolate y, I'll multiply by 7 over 2 to both sides. 2/7 times 7 over 2 equals 1. And now I'll distribute my 7/2 to the x and the 10/7. 7/2 times x is 7/2 x plus 7/2 times 10/7. Our 7s will cancel out to leave me with 10 over 2, which equals a positive 5. And that is all equal to y. Now I just have to set y as the inverse function. However, before I do that, I'm just going to flip this equation around so that I have y on the left-hand side. But as I do that, I'm going to set y as the inverse function, and then I'll put NOT to help us remember that we're just writing it in a different notation. So because this function is f of x, so we'll have the inverse of f of x equal to 7/2 x plus 5, or 5 plus 7/2 x. That is my solution in number 6. Now on to number 7. This f of x is going to be y, and we're going to switch y and x. So I'll have x equal to negative 3 over negative y minus 3 minus 2. Now I'm going to be solving for y. So I'm going to start by adding 2 to both sides to get that x plus 2 equals negative 3 over negative y minus 3. Now I want this y out of the denominator, so I'll multiply both sides by that denominator, negative y minus 3. So on my left-hand side, I'll now have negative y minus 3 times x plus 2 equal to negative 3. Now I don't want to distribute or FOIL these two binomials out because I want to isolate that y, so I'll simply divide by x plus 2. So I'll get that negative y minus 3 equals negative 3 over x plus 2. Now I'll add 3 to both sides to get that negative y equals negative 3 over x plus 2 plus 3. And I don't want this y to be negative, so I'll multiply by negative 1 on both sides to get that positive y equals positive 3 over x plus 2 minus 3. Now for my last step, I have to write y as my function notation. And because this is f of x, I'll have the inverse function of x equal to 3 over x plus 2 minus 3. That's my solution in number 7. Now for number 8, h of x, I'll write that as y, and then I'll switch y and x. So I'll have x equal to negative 2 times y plus 5. Now I'm going to be solving for y. So I'll do that by subtracting 5 from both sides to get x minus 5 equal to negative 2y, and then I'll simply divide by a negative 2 to get negative x minus 5 over 2 equal to a positive y. So now I'm going to rewrite this function up here as y equals negative x minus 5 over 2. However, I want to split this fraction up so that you can see the variable and then whether it's added or subtracted to a constant. So I'll have y equal to negative 1/2 x plus, because this negative is distributed to both the x and the 5, so when we're subtracting a negative, that's the same as adding a positive, and that'll be a positive 5/2. So now I'll just write y back as function notation. So because this function was h of x, we'll now have the inverse of h of x equal to negative 1/2 x plus 5/2. And that is number 8. For number 9, we have f of x equal to 5/3 x minus 5/3. So what I'm going to do is plug in y and then switch x and y. So we'll have x equal to 5/3 y minus 5/3. Now I'm solving for y. So I'll be adding 5/3 to both sides to get x plus 5/3 equal to 5/3 y. Now I'll multiply both sides by 3/5 in order to cancel out my 5/3. And I'll need to distribute the 3/5 to the x and to the 5/3. So I'll get 3/5 x plus 3/5 times 5/3 is a positive 1. So 3/5 x plus 1 equals y. Now I'm going to write that in function notation However, when I do that, I'm going to flip this equation around. So I'll have that y equals 3/5 x plus 1. So now my inverse of f of x is going to equal 3/5 x plus 1, or 1 plus 3/5 x. For number 10, breaking it down, we have y equal to 1 over x minus 1. So we're going to switch y and x. So now we'll have x equal to 1 over y minus 1. So I'll add 1 to both sides of my equation to get x plus 1 equal to 1 over y. Now I want y out of that denominator, so I'm going to multiply both sides by y. So I'll have that y times x plus 1 equals 1. I want y all by itself, so all I need to do is divide by that binomial that it's multiplied by. So dividing by x plus 1, I'll get that y equals 1 over x plus 1. And now in function notation, it would be the inverse function of f of x equal to 1 over x plus 1. That is my solution in number 10. Now moving on to the next section, on the second page, for numbers 11 through 14, it says to find the inverse of each function, then graph the function and its inverse. So let's get started in number 11 by solving for the inverse of the function. If f of x equals the fifth root of x plus 1 plus 2, remember our first step is to plug in a y. So we have y equal to the fifth root of x plus 1 plus 2. Now, our next step is to switch x and y. So x equals the fifth root of y plus 1 plus 2. Now we'll solve for y. We'll start by subtracting 2 from both sides to get that x minus 2 equals the fifth root of y plus 1. Now we need to get rid of this radical, and in order to do that, we're going to need to raise both sides to the fifth. So now we have x minus 2 to the fifth equal to y plus 1. So you can see that we got y plus 1 out of that radical. Now our next step, we're going to subtract 1 from both sides. So x minus 2 to the fifth minus 1 equals y. Now that we've solved for y, we'll write this back with the proper notation. So the inverse function of x equals x minus 2 to the fifth minus 1. So now you can see we've solved for the inverse of the function. Now we need to graph each of them. Let's start by graphing the function. Now we can use a t-table, or we can use a graphing calculator to help us find those values. I'm going to go ahead and use a graphing calculator just to make this a little easier on myself. So here we have our original function, the fifth root of x plus 1 plus 2. So you can see when we're at 0 in the x, we're at 3 in the y. So I'll graph that point, 0 in the x, 3 in the y. Then you can see our graph takes a turn. So when we're at negative 1, we're at positive 2. And at negative 4, we're at about 3/4. So 3/4. And going to the positive direction, at 6, we're at a little less than 3.5. So 6 in the x, 3.5 roughly in the y. And when we're at negative 2, we're at 1. So I'm going to write in a couple of these points to show you an easy trick. So we're going to have negative 2, 1, negative 1, 2, and 0, 3. Now I'll go ahead and draw my graph connecting my dots. Now let's graph the inverse of this function. So on my graphing calculator, I'll write my inverse, which is x minus 2 to the fifth minus 1. The intersection point is 3.34, 3.34, so roughly 3.3 and 3.3. Now you can see that we have points 3, 0, so 3 in the x, 0 in the y. We have point 2, negative 1, so 2 in the x, negative 1 in the y, and we have 1, negative 2. Here was 3.3, 3.3, 3, 0, 2, negative 1, and 1, negative 2. Now I'll go ahead and draw my graph. Now I'm going to write out the points that I've plotted. So we had 3, 0, 2, negative 1, and 1, negative 2. Now if you look, this graph is a reflection over the y equals x axis. And that is true for all inverses. So you can see 0, 3, we switched x and y, that became 3, 0. Negative 1, 2, switching x and y for the inverse, 2, negative 1. Negative 2, 1, switching x and y, 1, negative 2. That's why the intersection occurs at a point where x and y are equivalent. That was roughly 3.3 and 3.3. Let's continue on to number 12. For number 12, let's start by graphing the function. Our function was the opposite of 3 over x, so negative 3 over x plus 2. Now I'll go ahead and use my graphing calculator to help me plot my points. If you want to use a t-table, feel free to do that as well. So in this, we have a few easy points. We have negative 1, 5. We have negative 2, 3.5. So I'll graph those two. Negative 1, 5. Negative 2, 3.5. We have negative 3, 3. And we have negative 4, 2.75. So negative 3, 3, negative 4, 2.75. I'll go ahead and connect those points. Now, for the right side, we have 1, negative 1, 1.5, 0. We also have 0.5, negative 4. So just to make sure I get that curve more accurate. 2.5. So 2 in the x, 0.5 in the y. And we'll also do 0.3, 1, and 6, 1.5. So 3, 1, and 6, 1.5. Now we'll connect those with a curve. So just remember, the more points you use, the more accurate your curve will be. Now I'm going to solve for the inverse of the function. Y equals negative 3 over x plus 2. Switching x and y, I'll have x equal to negative 3 over y plus 2. So I'll subtract 2 from both sides to get x minus 2 equal to negative 3 over y. I'll need to multiply by y in order to get it out of the denominator. So I'll have y times x minus 2 equal to negative 3. And then lastly, I'll divide by x minus 2 because I want to isolate that y. So y equals negative 3 over x minus 2. Now in function notation, that's the inverse function of f of x equals negative 3 over x minus 2. Now without even plugging in points or graphing, we're going to go ahead and draw that new function. So remember, it's a reflection over the x equals y or y equals x line. So we're just going to be flipping the points. So first, let's reflect the first line we did. So we had negative 4, 2.75. So we're going to go to 2.75 in the x now and negative 4 in the y. Then we had negative 3 in the x, 3 in the y. So we're going to go to positive 3 in the x and negative 3 in the y. Then we were at negative 2 in the x and 3.5 in the y. So 3.5 in the x, negative 2 in the y. And then lastly, we had negative 1, 5. So now we'll be at 5, negative 1. So let's go ahead and draw this curve. Now we'll just replicate that second curve. So we were at 0.5 and -4, so now we're going to be at -4 and 0.5. Then we were at 1, -1, so now we'll be at -1, 1. Then we were at 1.5, 0, so we'll be at 0, 1.5. And then from 2.5 to 1/2, 2, and then 3, 1 to 1, 3, 6, 1.5 to 1.5, 6. Now I'll reflect that larger bottom curve. And now we've graphed our function and its inverse. And let's quickly double check plugging the inverse into our graphing calculator. -3 over x minus 2. And there we have it. It looks just like the graph we've drawn. Let's continue on to number 13. And number 13, I'll start by graphing g of x. However, I'm going to rewrite g of x so that's in slope-intercept form. So that'll be -3/5 x minus 10 over 5, which is 2. So now, using my slope and my y-intercept is -2, so I'll be at 0, -2, and then -3/5 for my slope, so going down 3 and 5 to the right, to the point 5, -5. So from 0, -2, we used our slope, going down 3 in the rise, and 5 over in the run to get to 5, -5, or we could have gone up 3 in the rise, and then negative in the x direction, so to the left, 5, to -5, 1. So remember, for rise over run, negative over the positive equals positive over the negative. Now I'll draw a line and connect those points since it is a linear equation. Now let's go ahead and find that inverse function. Switching x and y, and I can use either equation. So let's go ahead and use this bottom equation that's in slope-intercept form. I'm going to plug in y for g of x, so I'll have -3/5 x minus 2. Now I'm going to switch x and y, so I'll have x equal to -3/5 y minus 2, so I'll add 2 to both sides to get that x plus 2 equals -3/5 y, and then I'll multiply by the reciprocal of that fraction, so -5/3, and that will help me cancel out the -3/5 on the right hand side. So distributing that -5/3 to x and to 2, I'll get -5/3 x plus -5 times 2 is -10, and that's -10 over 3, so -10/3. That's equal to y. Now, because I have the same denominator, I'll write this as one fraction. So -5x minus 10, as opposed to adding a negative, I'll just subtract the positive, all over 3 equals y. Now, in function notation, the inverse function of g of x equals -5x minus 10 all over 3. Now, we can graph this. However, since we already have our points, let's go ahead and just flip those. So remember, we had -5, +1, we had +5, -5, and we had 0, -2. So that means -5, 1 will become 1, -5, 0, -2 will become -2, 0, and 5, -5 will become -5, 5. Now I'll draw a line connecting those points. And that's my solution in number 13. And if you want to double check, let's go ahead and plug in one of those values. Let's plug in -2 for x and see if we get 0 for y. So plugging in -2, we'll have -5 times -2 minus 10 all over 3. negative 5 times negative 2 is going to be a positive 10. So we have 10 minus 10 over 3, which equals 0 over 3. So it does indeed equal 0. So that's just a good way to double check. You can always plug in points on the line, and they should fit in that equation. Let's move on to the last problem in this section, number 14. For number 14, I'll use a graphing calculator to help me graph this. So for the function, we have 2n to the third, and that's minus 3. But I'll go ahead and write n as x for my graphing calculator online, because this graphing calculator is in terms of x. So 2x to the third minus 3. So let's graph a couple points. When we're at negative 1 in the x, we're at negative 5 in the y. So negative 1, negative 5. Then our graph intersects the y-axis at 0, negative 3. So I'll go ahead and start drawing my curve. And then it curves upwards, intersecting the x-axis at 1.145, 0. So 1.145, 0, and I'll write that so I don't forget that point since it doesn't fall nicely on a grid line. That was 1.145, 0, and then it continues on from there, never quite reaching 2 by the time it gets to 6. So I will not go past the line for x equals 2. Another point we can plot just to help us draw our graph is because it's a nice even intersection on those grid lines, 1, negative 1. Now it's time for the inverse. Let's start by graphing that since the points are fresh in our minds. So we have negative 1, negative 5. So instead of negative 1, negative 5, we're going to switch that to negative 5, negative 1. So negative 5, negative 1. And then, as opposed to 0, negative 3, we're going to plot negative 3, 0. So negative 3, 0. And then as opposed to 1, negative 1, we will have negative 1, positive 1. And then that 1.145, 0, we will get 0, 1.145. And remember, as we are going to 6 in the y, we never reached 2. The same thing applies for x. However, switch the values. As we approach 6 in the x, we never quite reach 2 in the y. And that'll just help us when drawing our graph. Now we have to actually see what the inverse function is. Y equals 2 times x to the third minus 3. So we're going to switch x and y. So we'll have x equal to 2 times y to the third minus 3. We'll add 3 to both sides to get that x plus 3 equals 2 times y to the third. Then we'll divide both sides by 2 to get x plus 3 over 2 equal to y to the third. And then lastly, we'll take the cube root of both sides in order to cancel out that exponent of 3. So we have the cube root of x plus 3 over 2 equal to y. But now we need to write this in our function notation. So the inverse function of g of n equals the cube root of not x plus 3, but n plus 3 over 2. And that's our solution in number 14. And if you want to double check, feel free to enter this in on a graphing calculator. Now onto our critical thinking questions. Number 15 says to give an example of a function that doesn't have an inverse. And quickly, what makes a function not have an inverse? Say we have our y and x axis. In order for a function to have an inverse, it must pass the horizontal line test, meaning that a horizontal line will only intersect ever at one point. So right away, a parabola would not pass the horizontal line test because you can see it intersects a horizontal line twice. Therefore, one function that doesn't have an inverse, f of x, is x squared. Now continuing on to number 16. It says find the inverse of f of x of the fourth root of x. So what we're going to do, we have y equal to the fourth root of x. Now we'll switch x and y. X equals fourth root of y. But now we need to isolate y, so we'll raise everything to the fourth in order to cancel out that fourth root. So we have x to the fourth equal to y. So in function notation, we will have the inverse function f of x equal to x to the fourth. But that's not our final answer. The inverse of f of x has a constraint on the domain, or a restriction on the domain. Inverse function f of x equals x to the fourth for values when x is greater than or equal to 0. That is key, because when taking the fourth root of x in our original function, x cannot be negative. That is not a real number. Therefore, our function also has to be for values where x is greater than or equal to 0. So negative x values are not possible. Therefore, x has to be greater than or equal to 0. Otherwise, it would be imaginary. And with that, we wrap up our function inverses worksheet. If you have any questions, please leave them in the comments below. And before moving on, don't forget to like, subscribe, and share. All likes and subscriptions, as well as sharing this video, is greatly appreciated.